Thank you for joining us today for a brief 20-minute interface demonstration of DataCore's SANsymphony-V software-defined storage product. DataCore software is a pioneer in the software-defined and storage virtualization industry, with over 17 years of development in a 10th generation enterprise storage product. With tens of thousands of deployments worldwide, SANsymphony-V is a product you can trust with your most critical asset, the data. Software-defined storage as we know it today has many different components, but fundamentally software-defined storage is all about abstraction of the data from the underlying storage hardware. Starting in 1998, the same year VMware started workload abstraction at the compute layer, which resulted in unprecedented flexibility across any x86 server, DataCore software started data abstraction at the storage layer, which resulted in equally unprecedented flexibility across any storage device. Today, nearly 2 decades later, both technologies stand as leaders in their own respective enterprise spaces. Over the many years of development, DataCore has gone far beyond simply providing data and storage abstraction services. While the importance of abstraction cannot be overemphasized, the resultant capabilities that arise from that abstraction are equally as important. Software-defined storage, which is made possible by abstraction, includes other very significant functions within the storage framework such as data availability, performance acceleration, efficiency, automation, and management services. I will give you a preview into each of these throughout the demonstration. One very important item to note is that while the features shown here appear to be very similar to other solutions in the industry, in most cases they have very different implementation methods, which set them apart from other solutions, giving the consumer the maximum benefit possible within their storage infrastructure. Also worthy of noting here is that while all of these capabilities have direct impacts on availability, performance, efficiency, and ease of management, the common denominator across all of these is the significant cost savings that is attributed to the DataCore solution not only on day one, but compounding year over year. Before we begin with a demonstration of SANsymphony-V, let's take a minute to outline where SANsymphony-V exists within the storage framework. There are 3 different deployment models depicted here. The first, in the middle, is a traditional storage model where there are very well-defined back-end storage, DataCore storage engine, and application server layers. The second, to the upper right, is a converged storage model where the back-end storage has been replaced by internal storage within the DataCore storage engine. Finally, the third, to the lower right, is a hyper-converged storage model where both the application and the storage reside within the DataCore storage engine. The reasons for choosing one deployment model over another will vary, but in general, the traditional model is typically used in large enterprise deployments where there is existing enterprise storage frames already in place. The converged model is typically used where a scale-out storage and consolidation model is desired. The hyper-converged model is typically used where a high level of consolidation and/or ultra-low application latency is required. In all scenarios, SANsymphony-V is directly in the I/O path between the application and the underlying storage hardware, providing a common set of enterprise storage and data services across any make and model of storage hardware. Additionally, there are also 3 components involved with storage presentation: the storage which resides within a DataCore disk pool, the virtual disks that are created from the disk pool, and the host servers which utilize the virtual disks for their respective applications. And finally, whether managing 2 nodes or 2,000 nodes, this can all be done within a single user interface globally across your organization. With the understanding of disk pools, virtual disks, and hosts, we can now proceed to the interface demonstration, which will align with these concepts. When the storage administrator opens the SANsymphony-V console, the Getting Started view is displayed. This view presents the most commonly performed storage administration functions. There are 3 docked sub-windows on the left-hand side of the screen and 1 docked sub-window at the bottom of the screen. The first sub-window in the upper left is the Server Group Connections window. This window displays a list of all known server groups within your infrastructure. To administer a particular group, simply double-click on one of the server group names. The second sub-window in the middle left is the DataCore Servers window. This window displays a list of all known server nodes within the currently selected server group. In version 10, a total of 64 DataCore nodes can reside within a single server group. The third sub-window in the bottom left is the Hosts window. This window displays a list of all known host or application server nodes within the currently selected server group. The fourth sub-window on the bottom is the Operations window. This window displays the most recent storage functions that have been performed along with their respective status. If a long-duration operation has been performed, the progress of the operation will also be displayed here. Along the top of the window, there are other buttons which display various details about the storage system. We will cover these later during the demo. For now, I will close the server group connections and hosts sub-windows so we can focus on the DataCore servers window. Focusing on the DataCore servers window, you will now see the individual nodes that are a part of the selected server group FTL headquarters. Expanding the node called Demo SSV01, you will see the major components that make up the DataCore node. These components are any attached and valid physical disks, DataCore disks, virtual disks, disk pools, and server ports. Similar to our architectural discussion earlier when I spoke about the relationship of disk pools to virtual disks, the interface is laid out in the same way. Let's start by exploring the disk pools section. Start by expanding the disk pool section and selecting the disk pool called Disk Pool 1. The first tab we see is the Info tab. This tab displays general information about the disk pools such as SAU or Storage Allocation Unit size, free space, max pool size, allocated space, and oversubscribed space. Since all disk pools are thinly provisioned, the SAU size represents the thin provision unit size. The SAU size is set when the disk pool is created and cannot be changed. SAU sizes can range from 4 megabytes to 1024 megabytes depending on the size of the pool required. SANsymphony can support up to 1024 pools per node and 8 petabytes of physical storage per pool. The second tab is the Settings tab. You can adjust the number of storage tiers for the specified pool as well as define specific space and I/O latency thresholds. The Space Preserved for New Allocations option is used for maintaining a certain amount of free space in each tier for new promotions of SAUs to each tier. This prevents first having to demote data to lower tiers prior to promoting the data to the higher tier. The third tab is the Physical Disks tab. This tab displays the physical disks which are members of the disk pool. Disk pool mirroring can be enabled here as well as auto-tiering. If a disk pool mirror is desired, then a compatible corresponding disk must be available, or unallocated, in order to assign it as a mirror member to an existing disk pool member. Auto-tiering is enabled automatically once there is at least 2 different auto-tiering index values assigned to 2 different disks. Auto-tiering index values can be assigned simply by right-clicking on the disk pool member and selecting the corresponding tiering value. Disks which have been assigned lower index values will represent disks with faster relative performance characteristics. Disks with higher index values will represent disks with slower relative performance characteristics. The tiering assignments tell SANsymphony-V which disks to use for hot active data and which disks to use for colder, less active data. The fourth tab is the Virtual Disks tab. This tab displays which virtual disks were created from the selected pool. The fifth tab is the Allocation View tab, or the disk pool heat map. This map shows where the hot and cold data resides relative to the various tiers within the disk pool. The hot data, or the dark blue lines, is the most frequently accessed data, and the cold data, or the light blue lines, is the least frequently accessed data. DataCore's auto-tiering mechanism is fully automated, sub-LUN, real-time, and both read and write aware. Once the administrator enables auto-tiering, there is nothing else for the administrator to do. The sub-LUN nature of this mechanism means that a more granular approach is taken to minimize the amount of data that needs to be promoted and demoted across the tiers, allowing the desired service level to be achieved in real time. Auto-tiering by default is read-only aware, but write-aware auto-tiering can be enabled on a per virtual disk basis through storage profiles. Additionally, disks can be added or removed from the pool non-disruptively. Performing either one of these operations causes the disk pool to become unbalanced. An unbalancing detected by SANsymphony will be automatically rebalanced in order to avoid hotspots from forming across the physical disks within the pool. This view, like other views within the console, contain performance and event tabs for monitoring performance metrics and events at a more granular level. Now that we have a functional disk pool, we can now create virtual disks. Next, we will look at how easy it is to create a virtual disk and serve it up to an application server. Now I will expand the virtual disk section of the tree. From here, a summary page will be displayed. This provides excellent insight into the health and configuration of the virtual disks that exist on this node. Note that the size column is the maximum size of the virtual disk. This can be changed if needed. The allocated space column represents the amount of actual data that is present within the virtual disk from a thin provisioned perspective. The DataCore servers column displays which DataCore nodes have responsibility for the virtual disk. The type column displays if the virtual disk is a single instance or mirrored disk. The storage profile column shows the virtual disk profile assignment currently in effect. The status column shows the operational state of the virtual disk. If you click on a virtual disk in the left-hand sub-window, you can see more detail about the virtual disk. Replace and move options are available on the screen, along with mirror status, host mappings, storage pool assignment, as well as any other relevant information depending on which functions have been enabled on the virtual disk. On the Settings tab, the virtual disk size and reserved space size are specified, along with many advanced options for the virtual disk. The Paths tab displays the front-end target mapping assignments as well as any mirrored path assignments that exist between the DataCore nodes. The Snapshots tab displays any snapshots that have been taken for this virtual disk. You can also create a snapshot from this screen simply by clicking on Create Snapshot located in the center of the window. Options for issuing a snapshot command for this virtual disk appear, which include which type of snapshot to take, either differential or full, as well as which disk pool to store the snapshot data. Once the desired values are set, simply click on Finish to execute the snapshot operation against this virtual disk. The Rollbacks tab displays any point-in-time rollbacks that exist for this virtual disk. Rollbacks are a function of SANsymphony-V's continuous data protection feature. I'm going to select a virtual disk which has continuous data protection enabled in order to show you this function. Now I can create a rollback simply by clicking on Create Rollback located in the center of the window. This feature creates a TiVo or DVR style recovery method for data, granting the administrator 1 second granularity when recovering a state of a virtual disk. First, choose the date and time to roll back to either by sliding the Restore Point indicator or entering a valid date and time value into the text box. Next, select Disk Pool, where the rollback data will reside. When finished, click on Create. Now a rollback volume is created which represents the state of the virtual disk at the specified date and time. This rollback can now be mapped to any available host server and the data recovered. The Replication tab displays asynchronous replication operations currently active against this virtual disk. This feature is outside the scope of this demonstration and will be covered in a later demonstration. Let's walk through how easy it is to create a virtual disk. To create a virtual disk, right-click on the virtual disks in the tree and select Create Virtual Disks. This will display a three-step process to create the virtual disk. First, assign a name to the virtual disk. This should be something descriptive, but also can be changed later if necessary. Next, select whether this is a single instance or a mirrored disk. Next, enter a virtual disk size and quantity. This is the maximum size of the presented volume. Because there is no penalty for presenting large volumes since all volumes are thin provisioned, you can be very generous with this value to avoid needing to resize it later. On the next screen, you will be asked for where the virtual disk should reside. Select the DataCore node and disk pool responsible for this virtual disk. The last screen is a creation summary screen and advanced options screen. This is where you can assign a storage profile, enable sequential storage, or continuous data protection. When complete, click on Finish and the virtual disk will be created. Because we created a mirrored virtual disk, both DataCore nodes responsible for the disk must be prepared. This usually takes 30 seconds to complete. Now that the virtual disk has been created and is ready for operation, the virtual disk can now be mapped to the host servers. To map the virtual disk which has just been created, right-click on the disk in the tree and click on Serve to Hosts. You will now see a window presenting all known host servers. You can either map to the DataCore nodes from which the virtual disk has been created, or to a host outside the DataCore node. In this case, I have a host contained within a host group. You can either map to individual hosts or to all hosts simultaneously contained within that group by selecting the host group name. In this example, I will map to the individual host. The next screen presents settings for changing the default target mapping values. You can be explicit with which target ports are used for mapping. If left to the default, SANsymphony-V will choose the best options for the virtual disk. When completed, click Finish. The virtual disk is now mapped to the host server. Now I will expand the DataCore disk section of the tree. DataCore disks are virtual disks which have been mapped back to the DataCore node itself. This is useful when running hyperconverged workloads where the application is co-resident next to the SANsymphony-V storage engine. Deploying applications in this way eliminates additional latencies that typically exist when going out over the wire to access the data. Since there is no wire when the application is running co-resident, there is a significant reduction in storage access latency. DataCore disks also represent virtual volumes served from other DataCore nodes. These virtual disks can be used in various ways depending on the deployment model chosen. In the physical disk section of the tree, any available and unallocated physical disks will be displayed here. To add a physical disk to a disk pool, simply right-click on the disk and select Add to Pool. Since all of my physical disks have been assigned to a disk pool, nothing is displayed here. However, if I click on Physical Disks, I can see the current disks and their respective disk pool assignments and statuses. On the DataCore node object in the tree, we will investigate specific settings related to the DataCore node itself. When you click on the Demo SSV01 node in the tree, you will see a summary page showing CPU, RAM, cache, OS, UPS, and write caching information, as well as product info in the lower portion of the window. Settings specific to this node can also be found under the Settings tab. Settings related to the replication buffer, configuration backup location, and map store location are found under the General Settings section. Settings related to caching are found under the Cache Settings section. And settings related to the management interface, replication buffer space thresholds are found under the Advanced Settings section. In the last section to be covered in this demonstration, we will review the settings specific to the DataCore server group. Click on the server group name located at the top of the tree called FTL Headquarters. From here you will see settings related to SMTP server settings, which are used for sending out email notifications via a mail server. Performance recording settings used to designate a local or remote SQL Server connection for storing collected performance data. And advanced settings for designating a support bundle relay as well as mirror recovery speed values. This completes the demonstration of the DataCore SANsymphony-V product. If you want more information or have questions, please visit our website at www.datacore.com or email us at info@datacore.com. Thank you very much.